Welcome. In this video, we're going to investigate absolute convergence and why it implies convergence. So a reminder that when we say a series is absolutely convergent, this means that the series of the absolute values of each term converges. So notationally, this is what we're talking about. We can look at a couple examples. So if we take an alternating series like this, the sum of -1 to the n divided by n squared, then the absolute value series is when we take the absolute value of each term. So that's actually just the series of 1 over n squared, no matter what our bounds are here. Now, in this case, we see that this series is absolutely convergent, the series I started out with, because of the fact that when I took the absolute values, I got convergence. But this doesn't always happen. That's why we have a notion of conditionally convergent. And basic examples of this, the most basic one is the alternating harmonic series, -1 to the n minus 1 over n. So this converges by the AST, but it's not absolutely convergent. So one of the reasons we like to look at absolute convergence is it's a 2-for-1 sort of result. And that's the theorem that I'd like to talk about. If a particular series, sum of a sub n, is absolutely convergent, then it must be convergent. So let's talk about why. Let's start out with the assumption that the series is absolutely convergent. So to assume absolutely convergent, what we're saying is that the series n equals 1 to infinity of the absolute value of a sub n converges. So now let's take the absolute value of a sub n series and let's add a sub n to it. For any term for which a sub n is negative, if we add it to its absolute value, we're going to get 0. And for any term for which a sub n is positive, we're going to add it to its absolute value and we're going to get 2 times its absolute value. So every term of this series, a sub n plus absolute a sub n, will be less than or equal to 2 copies of absolute value of a sub n. And the key thing about this is we've bounded our series, absolute a sub n plus a sub n, above by this one. So this is a positive series, and it's also convergent because we know that the sum of absolute an converges, and so the sum of 2 times absolute an should be 2 times the sum of absolute an, so convergent. The one in the middle here has to be a positive series, and we know it's a positive series by virtue of the fact that every term is greater than or equal to 0. So now we can talk about the series where you take the absolute value of an and you add an to it. Well, here's what we know. This series I've created is less than or equal to double the absolute value series. So this converges by the comparison test. Let me reiterate why. Because the series of 2 absolute an converges, and every term of my series is less than or equal to that. So now let's do some arithmetic. So we have that this series, absolute an, is convergent, and the series where we sum absolute an plus an is convergent. And they're both positive series. So I'm going to take the absolute an plus an one, and I'm going to subtract the absolute an. If I take 2 convergent series, I can subtract them, and therefore I can subtract them on the by term level. And I should get a convergent result. Well, now, if we do the subtraction, we've taken absolute an and subtracted it off. We are left with the series for just an. So it's kind of a neat, clever little proof. So the conclusion: showing a series converges absolutely tells me that the series itself converges. So let's end by doing one final example. Let's say I want to consider the series n equals 1 to infinity of cosine of 3n over n squared plus 1. And I want to know whether this converges or not. Well, cosine of 3n is always bounded above and below by -1, but it takes on all sorts of values in between. So I'm not going to have a lot of luck trying to use other series because that numerator just won't, it keeps oscillating. So what I can do is I can try to find out if it's absolutely convergent. Instead, I'm going to look at the sum of the series cosine of 3n over n squared plus 1 absolute value from 1 to infinity. Well, now I can do this via comparison test because the absolute value of cosine of 3n is less than or equal to 1, and therefore the absolute value of cosine of 3n over n squared plus 1 is less than or equal to 1 over n squared plus 1, and then I can bound that above by further shrinking the denominator with 1 over n squared. So because the absolute value made this a positive series, I'm going to be able to use a positive series theorem, namely the comparison test. So since the sum of 1 over n squared converges since p equals 2 is greater than 1, by comparison test, my series is absolutely convergent, and therefore it's convergent.